Okay, we're going to start a new chapter now called equilibrium. And here we're going to focus on a type of reactions that we haven't really looked at too carefully, which is called reversible reactions. Before we can talk about reversible reaction, I want to talk a little bit about irreversible reactions, which are reactions that appear to only go in one direction, and that is towards the product side. All the reactions we talk about in Chem 11 are irreversible reactions, or we had made the assumption that they're irreversible, right? So things like combustion reaction, they tend to go just one way, that once you make all the product, then you're done. The other situations where we see these irreversible reactions are reactions with limiting reactant. Remember that typically the reactions is considered done when there's no more limiting reactant. It turns out that there's actually a large number of reactions. In fact, you can kind of think theoretically that all reactions are reversible, which just means that they don't end when products are formed because the products are able to convert back to the reactant. So in other words, you typically just think of reaction as going in the forward direction, going only from reactants towards product. But of course, when we discuss mechanism, we realize that some of these products, as they're formed, there's really no reason why they can't, at that particular temperature, have enough kinetic energy to collide with each other and then reform the reactant from those collisions. So that's what we call the reverse reaction. Now, over time, what's going to happen, of course, is because the concentration of the reactant decreases since you're making some product, the forward reaction rate will also decrease because the forward reaction rate depends on the concentration of reactant. On the other hand, the reverse reaction rate should increase because you start to make more and more product. And eventually, there is going to be a concentration where the reaction rates are equal to each other. So the forward rate is equal to the reverse rate. And that's the point that we refer to as a dynamic equilibrium, or sometimes just called chemical equilibrium. So that's the point when you no longer see a change in concentration of reactants or products over time. So this plot shows what we will observe. This is a reaction where NO2 goes to form N2O4. And so at the beginning, there's a lot of reactant, and the reactant slowly decreases. And then there is no product at the beginning, but then they slowly increase. As you monitor this, you'll see there is a point in time, which is indicated by this line right here, where the concentration of the product and the reactant remain constant over time. They don't change over time. That's what we call equilibrium. So when we reach this point, that vertical line, that's the time when we say that reaction has reached equilibrium. We have a symbol for this double-headed arrow. So you'll see it written this way sometimes, or sometimes with just these half arrows that I've typed in the lecture notes, but that indicates that the reaction is reversible. Okay. Now, sometimes this situation happens with substances that are the same but in different phases. So, for example, at the melting point of water, you have ice and water both coexisting and they interconvert to each other. So this is solid and liquid states of water. That equilibrium we would refer to as physical equilibrium because it's just an interchange of two physical states. We call this condition dynamic equilibrium because the products and the reactants don't stop reacting at equilibrium. The reactant is still converting to product. The product is still converting back to reactant. It's just that the rates at which they're doing that conversion is equal to each other. Okay? They're actively moving around. Of course, we didn't know initially that that's the case. We have to do an experiment to figure out that the species is actually dynamic and doesn't just stay static. So the experiment is illustrated right here. So let's say you have a reaction that has reached equilibrium. An example of this is an insoluble salt that has both the precipitate and the ions floating in solution. Both solution form and precipitate form exist. The precipitate is a product, the solution is the reactant. At that point, you can add some radioisotope form of the solution. So what we've done is we've added reactants that we can observe due to its radioactivity. That's illustrated by this red color solution on the top right. Now, since the reaction is already at equilibrium, in theory, if it's a static process, that means that that radioisotope will just stay there. It wouldn't go anywhere. But it turns out what we actually observe is the picture on the right. If you let that reaction that is at equilibrium sit over time, you see that some of those radioisotopes now form the precipitate at the bottom, indicating that even though the reaction is already at equilibrium, the reactants are actively converting to product. So that's the reason why we know that this equilibrium equilibrium position is not a static position, but it's a dynamic position. Are products and reactant concentrations equal at equilibrium? The answer, of course, is no. We don't need them to be equal. All we need to make sure of is that they don't change over time. That's what we mean by equilibrium. So it turns out that there's something interesting about this equilibrium position. We can tell from experiment that we reach that equilibrium position when the concentration no longer changes over time. And so these three plots are showing you three different equilibrium positions. But I also want you to focus on the starting conditions. Here NO2 is red and N2O4 is green. So in the first one, we start with just NO2, and then over time, we notice that the reaction reaches this equilibrium position right here, where there's less NO2 compared to N2O4. In this case, we started the reaction with 0 N2O4. In condition 2, we start with no NO2, but we have some N2O4 present. Because the reaction is reversible, some of those N2O4 actually converts to NO2, and eventually they reach an equilibrium where there's more N2O4 compared to NO2. And then lastly, we start with both NO2 and N2O4 present. And then at some point they reach this equilibrium position. And again, you see that there's more N2O4 than NO2. So a couple of scientists noticed this pattern. It seems that when the reaction reaches equilibrium, there is a constant. And the constant is a function of the ratio of the concentration of products and reactants at equilibrium. So in all three cases, even though you start at different starting positions, the concentration of N2O4 always ends up being higher than NO2 at equilibrium. Is there a specific number that we can calculate that will tell us that a reaction has reached equilibrium? And it turns out that there is, and we call that number the equilibrium constant. Let's see how we calculate that number. So this table shows the same reaction with 5 different initial conditions and 5 different equilibrium conditions. The first proposal was actually just to calculate the ratio of products to reactant concentration. It turns out that when you do that, you find that the numbers keep changing. And the idea is that there has to be a constant that happens when the reaction reaches equilibrium that will give you the same number every time. But if you actually calculate it this way, you do get the same number every time. So the reaction is N2O4 goes to NO2. And there is 2 coefficient there to balance it out. It turns out that when you take the ratio of NO2 raised to 2 divided by N2O4, you get the same number every time, as we showed in that table. What is NO2 raised to the power of 2? Well, it's just the coefficient of NO2 in that reaction. And then N2O4 has a coefficient of 1, so when it's raised to the power of 1, then it's just itself. Now, it turns out that this is true for all reactions at equilibrium. You can calculate this constant, and this is what we call the equilibrium constant. In fact, this discovery is referred to as the law of mass action. Just saying that reactions will reach a point when the ratio of the concentration of product and reactant raised to their coefficient will give you a constant. And so if you have a generic reaction like this, AABB goes to CC and DD, where the lowercase letters represent the stoichiometric coefficient, you can calculate the equilibrium constant for that reaction by using this expression right here. Very important though, the concentration you have to use here has to be the equilibrium concentration. Okay, so you can't use any other concentration, right? So you want to be really careful with this, because remember that this is initial concentration. So you don't want to use those numbers. You want to calculate K only with numbers here, the equilibrium concentration, which is when the concentration no longer changes as a function of time. Okay, so don't use any other number but the equilibrium concentration to calculate K.